Blackbody radiation is an extremely fundamental and inherently quantum mechanical phenomenon. Its description is intimately linked to the discovery of quantum mechanics, and its effects have profound implications. Let's explore one of those implications, namely, how it helps us explain the climate that we observe on Earth.
Okay, the sun is a hot sphere of burning plasma. We know how big it is, we know its radius, so we can calculate its surface area. Right? And the sun also emits light with a spectrum that's close to that of a black body at the temperature of the sun's surface. So we know what a black body radiation distribution looks like. It's described by the Planck radiant energy distribution. That's nice because we can derive from that the maximum wavelength here is related to the surface temperature of the emitter. That's known as the Wien displacement law. So if we measure the maximum wavelength of this distribution, we can figure out the surface temperature. And from the Stefan-Boltzmann equation, right, once we know the temperature of an emitter, we can calculate the irradiance of that emitter, the power per unit area that's coming off of the black body emitter. The emissivity here, that's 1 for a black body, and the Stefan-Boltzmann constant, sigma, that's also known from experiments. So now if we know the spectrum of light coming off, we figure out the temperature, we figure out the irradiance, we can multiply by the area and calculate the power emitted from the sun. And it's a huge number, 3.8 times 10 to the 26 watts. Now the light that's coming from the sun, right, that's emitted by the sun, it's expanding out in this sphere that's getting ever larger until it finally intersects with the Earth out here, the blue planet. All right, and the Earth, we know the distance away from the Earth. We know that it intersects only a small amount of the photons, right? So of all the photons that are going out into this huge sphere, only a small fraction of those is actually hitting the Earth. And even of the Earth's surface, right? We know the Earth's surface, we know the surface area of the Earth because we know the size of the Earth. Only about a quarter of that is being illuminated by the sun at any time. Of all the photons that hit the Earth, not all of them are absorbed, right? The Earth has a reflectivity known as its albedo, call that alpha. It's about 30% of the photons bounce off of the Earth, right? So if we want to calculate how hot is the Earth, well, we know that it's steady state, right? There's this emission of light from the sun. We've seen that distribution. Okay, there's emission of light from the sun. So there's a certain power that's being absorbed by the Earth. And then the Earth itself is a black body, and it emits at a much longer wavelength, right? Not as high energy, not as high intensity because it's not as hot as the sun, right? But at steady state, the power absorbed by the Earth from the sun has to equal the power emitted by the Earth from its own black body radiation. Well, can we relate the power absorbed by the Earth to the power emitted from the sun? And indeed we can. We need to know how much was reflected, so we measure the albedo, and we can know how much is reflected, and we need that dilution factor, right? That not all the photons that are emitted into that whole sphere actually are intercepted by the Earth. And so we can put in the reflection factor, we can put in that dilution factor, right? That small solid angle that's absorbed, that the Earth actually intersects, and we get a formula relating the power emitted from the sun to the power absorbed by the Earth. Now the power emitted by the Earth as a black body, again, that's related to the temperature of the Earth, right, to the fourth power. Now we have expressions for both the power emitted by the Earth and the power absorbed by the Earth. We set these two equal to each other, solve for the temperature of the Earth. And indeed, simply by knowing the temperature of the sun, the radius of the sun, the albedo of the Earth, and the distance of the Earth from the sun, we can estimate the mean temperature of the Earth, 248 Kelvin. How's that look compared to the real answer? The real answer is about 288. At least it was in 2020. What a year that was. So with these really simple 3-4 lines of equations, we're able to get an answer that's about 85% correct, right? Not too bad for a back of the envelope calculation. And indeed, the difference between these two must be related to something we've left out. What we've left out is known as the greenhouse effect. Arrhenius, back in 1897, said, hey, wait a second, there should be a greenhouse effect going on. There are atmospheric gases, right? That there's this emission of light from the sun absorbed by the earth, and then emission from the earth, and some of this radiation emitted by the earth is absorbed by gases in the atmosphere. Now, the most important of these is H2O, but there are some other gases that can add to the warming capacity of the atmosphere, right? Because for this emission of light from the earth, water is the most important gas that absorbs some of that light and heats up the atmosphere. That's really important because the amount of water in the atmosphere is more or less in steady state, right? If the air gets saturated and there's too much water in the earth, we know what happens. It snows, it rains, right? If there's too little water in the atmosphere, well, luckily 70+% of the earth is covered by water, and so more water can evaporate from the oceans, lakes, rivers. So the amount of greenhouse gas warming from water is more or less constant. Got to worry about clouds and things like that, but also there are other things that we can add to the atmosphere, particularly CO2 and methane, and when those go into the atmosphere, they can increase the amount of greenhouse gas warming. And we don't get much CO2 snow around here, so we know that those things aren't saturated yet, and we can add more of those and enhance their warming effect. So, take-home message from today's lecture: calculating the mean climate of the Earth is pretty easy once you understand black body radiation, steady state, and a bit of geometry, right? Estimating the greenhouse gas effect, that's also fairly easy. A simple model for that. You can find that in the supplementary exercises posted in the instructor's companion website for the book, right? You can calculate the mean climate really easily, as we've seen. Same for the greenhouse gas effect. But of course, we don't live in the mean climate, right? We live in a seasonal and daily weather. And calculating mean climate, while that's easy, calculating weather is hard because it's a stochastic process, and deviations from the mean are what make the seasons and storms and all of the challenges that are posed by climate change.